Good afternoon, everybody. Welcome to lecture. So, big news, we got an exam on Monday. Here's a survey question that is interesting. Ring, is it aromatic? Is it anti-aromatic? Is it non-aromatic? So what you're told in this question is assume the ring in the structure below is plain or flat and decide whether it is non-aromatic, anti-aromatic, or aromatic. So this is one way in which you'll see these questions posed to you is telling you, okay, straight up, the ring is flat. If you assume that, what else can you tell me about the molecule in that state? Because that's a confirmation this molecule could adopt. So what it boils down to is you got to look to see if it meets all the criteria for being aromatic or anti-aromatic, and you got to see, well, is it a ring? And the answer to that is yes. Is it flat? Well, you're told that it's flat, so that checks out. The third thing that you have to look for is it fully conjugated with an uninterrupted ring of overlapping p orbitals? And the answer is yes, because that nitrogen is sp2 hybridized and it has a p orbital on it, and that oxygen is sp2 hybridized and has a p orbital on it. And I know that because of that XYZ rule, where you go XYZ, XYZ, and so then the next thing is how many pi electrons does it have? So let's count them. You count 2 for every double bond in the ring, which is going to get us to 6, but then what do you do with these heteroatoms? And so this is a question that's still coming up and people are wondering about it, is do they count as pi electrons or not? In this case with this nitrogen, there's that lone pair exists in a p orbital because of this XYZ system and the fact that it's using its sp2 orbitals to make bonds to 3 different atoms. The place to put those electrons, the only place to put them is in a p orbital. So those count as pi electrons. So that would get us then to 8. But then there's an oxygen, and that's also an sp2 hybridized oxygen. So it's an sp2 hybridized atom. It has 3 hybrid orbitals, 3 sp2 hybrid orbitals. It uses those to make a bond to carbon, another bond to that carbon, and then one of the sp2 orbitals holds one of the lone pairs. So one of the 2 lone pairs in oxygen is in an sp2 orbital and doesn't count as pi electrons, but the other one does sit in a p orbital and does count. So for oxygen, one of the 2 lone pairs counts, and for the nitrogen, it also counts. So when you do the math then, or you have the counting on this one, you get 6 for the double bonds, 8, and then 10. So it's got 10 pi electrons. That's a multiple of 4n plus 2. So this molecule, when it's flat, would be aromatic. So you want to check the aromatic box. Okay, and then there's another question down here that asks about a carboxylic acid. This is ibuprofen. So ibuprofen is an interesting carboxylic acid. It's also got an aromatic ring in it, but it's telling us here the pKa value for that acid is 4.9. So that's a measure of its acidity. Remember, the lower the pKa value, the stronger the acid is. And then we're getting a series of bases here, and it says which of the bases below are strong enough to deprotonate it. And then it says for reference, the conjugate acid pKa values are listed below in parentheses. So we're given 3 bases. We're given sodium hydroxide, sodium bicarbonate, baking soda, and then we're given this trifluoroacetate molecule, and we're told the pKa of their conjugate acids. So trifluoroacetate, the conjugate acid is trifluoroacetic acid. It has a pKa value of 1. That's a very strong acid, which means that the base is a very weak base. Over here we've got sodium bicarbonate. Its conjugate acid, carbonic acid, has a pKa of 6.4, which is kind of a medium strength acid. And its base is kind of a medium strength base, not real strong, not real weak. And then we got sodium hydroxide here, which has got a really its conjugate acid is water. Its pKa value is 15. You could also say 14. I mean, it depends on what book you look at, but 14 is probably more accurate. But either way, that's a pretty weak acid, which means that's a pretty strong base. So to tell, is it strong enough to deprotonate this carboxylic acid? It has to go from stronger acid to weaker acid. So when you use a base and it deprotonates this and it forms a conjugate acid, the conjugate acid must be weaker. So the conjugate acid has to have a bigger pKa value than 4.9. This one definitely does. Hydroxide it has a conjugate acid whose pKa value is a lot bigger, 15. So this is definitely strong enough. It's way overkill, actually. It's a real strong base to pull off this acid. Sodium bicarbonate is a lot closer. Its conjugate acid is 6.4, but that's still a pretty big difference, and carbonic acid is a weaker acid than this. So use sodium bicarbonate, it will deprotonate the carboxylic acid. The equilibrium isn't quite as big, but it still favors products by a lot. And then there's this one whose conjugate acid, this base's conjugate acid is very, very strong. So this one would not work. That is not a sufficiently strong base to pull off that proton because it's in the wrong direction. You'd be going from a weaker acid to a stronger acid, and that is something that you don't see molecules doing. So the answer to this one is the bases that are strong enough are number 1 and number 2, so the answer is A. Question.
How big of a difference would the pKa's have to be so you'd be able to do it?
Good question. So the question is how big of a difference does it make? So what you can say is if the pKa values of the acid and the conjugate acid are the same, then you'd get equal amounts at equilibrium. If there's a 1 pKa unit difference, that's a factor of 10. So it'd be a 10 to 1 favoring the one that goes to the weaker acid. If it's 2 pKa units, that's 100 to 1. So each pKa unit is a factor of 10 because it's a logarithmic scale. So this one, if you're looking at 15, that's 10 pKa units, that's 10 factors of 10. So that is a really, really large number. It means that the equilibrium is essentially all products. It would go to deprotonate this and form water as the conjugate acid to the point where there's there'd be like basically no starting material left over. This one isn't quite as product favored. It's like about 1.5 pKa units, so it's 10, maybe like 15, or maybe like no, sorry, not 15. Between 10 and 100 would be favored. The equilibrium constant would be somewhere between 10 and 100. So that's it's still really big equilibrium constant, but it's not like billions. And this one would be extremely unfavored to the point where reactants would be favored by like 5 factors of 10. So, or 4 factors of 10, I should say. So it really is. It's kind of like a measure of acidity and just comparing, how much you get a stronger acid or a weaker acid and by how much. So it was a good question. Okay, the other thing is there's an exam coming up. So I'm going to hit that exam page just to make sure you're aware of it. Down at the bottom, I'm going to look at this exam info page here and just point out what's going on. This is information about the exam. It's going to be Monday. It's going to cover the things that are discussed in the syllabus, and there's some molecules of the day here that have been introduced and talked about over the course of the last few weeks. Those will be on there as a matching exercise. And then there's some old practice exams down here too that we will talk a bit about if, depending on how much time we have, we'll go through some of those. Those are really good practice. So that's what's coming up. Any questions on the exam? Okay, let's go do some carboxylic acid stuff. Oh yeah, the recycling symbols, there'll be a little bit on recycling symbols. Yep, so know what they are, know the polymers. So it went 2, 3, 4, 5, and 6. And there's usually a hint about what it is below the recycling symbol. There's like a letter or a series of letters like PP is polypropylene and PS is polystyrene below the recycling number, which maybe means less to you. But yeah, and then if you see a polymer, trying to figure out what kind of monomer it could come from. Okay, so carboxylic acids, we just have a little bit of material to talk about yet in carboxylic acids that's new. Actually, it isn't even really new. It's more review from Organic 1. So let's talk about what makes an acid stronger or weaker. I'm going to give you 2 carboxylic acids, and then we're going to discuss what makes maybe one stronger than another. So here's a carboxylic acid. It's acetic acid. This is a real common carboxylic acid. It has a pKa value for that proton that is equal to 4.8. Then let's look at a Another carboxylic acid that's pretty similar looking, but has a chlorine on it. So in place of one of the hydrogens, there's a chlorine. Now the pKa value for this one is 2.9. So this is a stronger acid, and by almost 2 pKa units. So this is about 100 times stronger acid than this one. So the chlorine is definitely making a difference. And so we need to talk about why, what's going on with that. How is it that chlorine affects the acidity of this proton? And the chlorine's over here, the hydrogen's over here, but they're somewhat close. And here's the thing: there's this inductive effect that we talked about before. So chlorine's an electronegative element. It pulls electron density towards itself, and it develops a partial minus charge. Carbon then develops a partial positive charge. That carbon then pulls electron density away from that one. So there's a through bond effect where the chlorine is pulling electron density. It affects that carbon, which pulls electron density from this carbon, which pulls electron density from that oxygen, which ultimately pulls a bit from that hydrogen. And so that hydrogen was partially positive before, but it gets a little bit stronger partial positive charge on it now, so it's a little bit more acidic. It's more attractive for a base to pluck off. And if you take a look at what you get for conjugate base when that proton is abstracted, the base, if a base comes by and grabs that proton, and now there's an O minus here, there's the chlorine, hydrogen, hydrogen. This is a more stable anion because of the chlorine. More stable anion due to the chlorine. The chlorine is, again, it's pulling electron density towards it, away from this carbon, away from that carbon, and ultimately away from that oxygen. So it's like some of the load of the negative charge has been taken from this oxygen and transferred to the chlorine. So chlorine, through the sigma bonds here, is sucking some of that extra electron density up. And this is what's called an inductive electron withdrawal. Inductive effect just means through sigma bonds. So it helps a little bit to have a chlorine on here. It makes this more stable, and so it's a more stable anion due to chlorine and a weaker base because of the chlorine. And since this is a weaker base, its conjugate acid is therefore stronger. Stronger acid due to chlorine. So the chlorine has an impact. And there are more things you can do with this. So like, for example, in addition to just like, say, one chlorine, if you put multiple chlorines on, each one has an impact. Each one makes it a little bit more acidic. So like, for example, let's take a look at some trends in acidity. And this is one of the things that you'll see on the old exams, and there'll be a question like this on the exam on Monday, asking you to rank some carboxylic acids in terms of like how strong of an acid are they. So if you've got, like, for example, acetic acid, this is not as strong an acid as chloroacetic acid. And then if you put 2 chlorines on the carboxylic acid, it's an even stronger acid. And if you put 3 chlorines on the carboxylic acid, it's an even stronger acid. So I think you can kind of see the pattern, hopefully, that strongest acid, and this one is weakest acid in this list that I'm providing for you. and it increases going left to right. And it's because of this inductive withdrawal of chlorine. No chlorines, you get no withdrawal from the functional group. One chlorine withdraws a little bit of electron density, makes it a little bit more acidic. Two chlorines withdraws more, makes it more acidic. And trichloroacetic acid is really quite a strong acid because it's got three chlorines that are pulling electron density away and making that H more partially positive. So, so one of the trends is more electronegative groups makes for a stronger acid. If 1 is good, 2 is better, 3 is best if you're going for strong acid. The more electron withdrawing groups, the stronger the effect. And the whole point of this is chlorine is an electronegative element. You could get the same job done by fluorine, even to a greater extent, because fluorine is more electronegative than chlorine, for example. So, that's one of the things that happens. Electronegative elements have an impact on acidity for that reason. Now let's take a look at what happens when the proximity of the electron withdrawing group changes. So one of the things about the inductive effect, and we looked at this when we were looking at NMR spectroscopy and we were studying chemical shifts, and we saw what happens when you put an electronegative group on a carbon and the hydrogens that are attached to it are deshielded a lot. The hydrogens on a carbon next door are deshielded just a little bit. And carbons that are further away, their hydrogens hardly are affected at all. And so that's because this inductive effect is distance dependent and it doesn't like transfer forever. So every step you get further away from the electronegative group, the weaker it gets. So here's an example of a series of carboxylic acids. See, I'll do 1, 2, 3, 4, 5. So I'm going to draw 5 carboxylic acids here with 5 different positions of an electronegative element. Fluorine, fluorine, fluorine. So they all have fluorine on them, but the fluorine is not the same distance from the carboxylic acid. This is the strongest acid because the electronegative group, the thing that's pulling electron density away, is close. It's only, it's 1, 2, 3, 4 bonds away from the hydrogen. You get over here and it's a weaker effect because it's further away, and the electron withdrawing impact of the fluorine is muted a little bit by distance. So this is 1, 2, 3, 4, 5 bonds away from the hydrogen. That's weaker. And then over here, it's even weaker because this one is 6 bonds away, and that's a pretty long distance. So this would be the weakest acid in this list. So it's about number of electronegative groups, how electronegative are they, and then how close are they. Those are the big factors that influence some differences in carboxylic acid acidity. Yeah, there's a question.
So this kind of goes back to like yesterday when we were talking about like with the R group attached to the other side. Does the size of the R group matter?
Good question. So there's a question about what do the R groups contribute? So here's an example of that. The R groups effectively donate a little bit of electron density, and I do have an example of this. This carboxylic acid that has 3 methyl groups attached to the carbon that's attached to the carboxylic acid, they have a very slight electron donating effect. So rather than pulling electron density away, they push a little bit of electron density in. And that tends to make the partial positive on the hydrogen a little weaker. It's a little less acidic as a result. So it's electron, instead of electron withdrawal, it's electron donation. So that tends to affect acidity in the other direction. So this is a bit weaker acid due to alkyl groups donating electron density. So the result is it's a little bit weaker acid than the carboxylic acid that doesn't have those. So we've got, for reference, carboxylic acid with some H's on it. The pKa value of that hydrogen is 4.76 is the number I'm going to put up. 4.76 is the pKa value for that H. Over here, that H has a pKa value of 5.01. It's not a dramatic difference. It's not even 1 pKa unit. It's not a factor of 10. It's less than that, but it's measurable. So and that's what's going on is these groups are donating electron density, so makes it less acidic. So yeah. And the size of the R group doesn't really matter. It's methyl here, but ethyls and propyls would have pretty much the same effect because they all have the same electron donating capabilities. Carboxylic acid, when it has methyl groups or alkyl groups attached to the carbon that's attached to the carboxylic acid, they donate electron density in. They make it a little bit less acidic. It's a little bit weaker acid due to the fact that they're donating electron density. It is a pKa of 5.01, whereas without the methyl groups, it's a bit stronger acid at 4.76. Okay, any other questions about carboxylic acids? So that's all the material I have to talk about with them. And so now I thought maybe we could go through some stuff from old exams, review a little bit. So let's talk about that. Because it's been a little while since we've talked about things like radicals and chlorination and bromination. And, I don't want you to, forget about that stuff or have it be too long ago so that you don't remember it well enough to do well. So I've got old exams, and usually what I do is go over the one I gave to students the previous semester. So this is exam 2 from fall semester 2024. And one of the questions asks about, it gives a series of radicals, and it asks about radical stabilities. And it introduces a class of molecules called the bisabolines, which are really fragrant molecules that are found in the essential oil of a lot of different plants. But here's one of them. There's a radical right there. Another one that's shown here is like this. It's very similar structure, but the dot is right there. And then the last one is a molecule that looks like this. It's got the radical in yet a different spot. Right there. Okay, so which one of these is the most stable? So radical stability, two things you got to remember. Substitution affects it. So more substituted radicals are more stable, and resonance is a huge, probably most important thing. So if you see resonance stabilization, that's kind of the key. That'll make it the most stable. This one has resonance, a resonance structure. You could take that dot and delocalize it and put it out there. I could draw a resonance structure where I draw fishhook arrows and I delocalize the dot to that carbon. So this has one resonance structure. Which is going to make it really nice and stable. But this one is better because this one has two resonance structures. It's next to not just one double bond, but two double bonds. So in addition to, and what I should say here is one additional resonance structure. One additional resonance structure. In addition to this resonance structure, there's one more. Here, in addition to this, there are two other resonance structures. Two additional resonance structures, and For this one over here, there's no resonance structures. So this one is the least stable, that one's the most stable, and the one over there on the left is kind of in the middle. Does that make sense? All right, let's go. The next one's a chlorination example, and let's chat about that. So you're given an alkane and asked to draw some chlorination products. This alkane is dimethylcyclobutane. And the question says, there are 4 unique monochlorination products, including stereoisomers that form when this molecule is treated with chlorine and light, which provides activation energy to break the chlorine into 2 radicals, which is the initiation reaction, and then propagation reactions produce products. So draw any 3 of these. So what I'm going to do is draw all 4 because, yeah, let's do it. So you got to figure out where are there H's that could be abstracted. We've got methyl groups here, methyl here, methyl here. So let's go pick on one of those first. Okay, there is one right there. Now, did I make a new stereogenic center here? Right, I see some heads shaking. So there's no stereogenic center here, so I don't need to draw dashes and wedges. I don't need to worry about what stereoisomer is formed because it's achiral. So that's one. And then there are the possibilities over here on the ring. Let's go to the far corner and just deal with that one right now. There's a chlorine here. If we put a chlorine there now, how about that one? Is there any possibility for stereoisomers here? And if you put it as a dash or you put it as a wedge, it wouldn't make 2 different molecules. It would make the same molecule that could be superimposed on the other by just rotating. So you don't need to put a dash or wedge there. This is an achiral molecule. It has an internal mirror plane of symmetry. Same thing with this one. It has a mirror plane of symmetry too. Yeah, question. Good question. So the question is would you get penalized if you indicate a dash or wedge here? No, I would be fine with that. I wouldn't, you can, there's nothing wrong with it. It's just you don't need to. So it truly does. The true structure of this, the chlorine is on a dash or wedge and the hydrogen has got the complementary bond, either a dash or wedge, depending on what you drew here. So, I mean, the real structure of it is, it's not a flat molecule, but it's just what are you required to show versus what's required to convey meaning, and here dashes and wedges aren't needed, but you can still add them if you want. Another question that comes up is what happens if I duplicate a molecule? Usually on exams, I don't take off points for that. I'll just say, I'll write a note saying these 2 are the same and I'll put an arrow towards them or I'll circle them or something. But I don't deduct points for that. It's more of a problem if you're looking for 4 stereoisomers and you draw a duplicate and you think you've got all 4 because you're seeing 4 structures there, but 2 of them are the same, then that's a problem. So it is important to know it, but there's no penalty for duplicating structures, generally, unless I say it in the directions. All right, and then we've got positions here and here that we need to think about. So let's just pick one of these and draw a CL on it. Okay, what do you think about this one? That did make a stereogenic center. This carbon right here has 4 different groups attached. There is a hydrogen, so there's a chlorine, there's a hydrogen that's not being shown. There is a ring position with 2 methyl groups on it and a ring position with 2 hydrogens on it. So this one is a stereogenic center and you have to indicate stereochemistry. One of the options would be that, where the chlorine is got a wedge bond orientation, it's closer in space to you. The other possibility is the one where the chlorine is on a dashed bond, it's pointing away from you. And these are 2 stereoisomers. Now, if you were to do the substitution on that carbon, since there is a mirror plane of symmetry in the molecule, doing a reaction on this side, there's a corresponding reaction on the other side. In other words, there aren't more unique molecules that you will form by putting a chlorine on that carbon. You'll simply reproduce these two molecules in a rotated form. So these are the 4 unique substitution or chlorination products, monochlorination products. And for this question, you could do any 3 of them. Questions on that one? All right, the next one is a resonance structure drawing problem. It gives you a radical that's resonance stabilized and allylic radical, and it's going to ask you to draw a resonance structure for it. So this is good review on how to handle that. So this radical has structure where there's, and I'll draw a CH2 here, a CH3 up here. There's a dot right here. So if you were looking at this molecule from a stability perspective, you might say primary radical isn't very stable. However, there's a double bond next door, so there's a resonance structure that makes it really quite stable. And to draw that resonance structure, what you want to do is use the half-headed fishhook style arrows, take that dot, and then take one out of the pi bond and pair them up to share them here to make a double bond between those 2 carbons. And then the other electron in the pi bond goes to that carbon right there. So then when you draw the structure of the product that you get out of this electron pushing, it gives you the radical on a different spot, in a different position on a different atom. And that delocalization is what makes for a more stabilized radical. It's not stuck on one carbon. The instability is spread out over multiple different atoms. So that's kind of the key idea with resonance, is that if you spread out a charge or a radical, it helps stabilize things. All right, moving on to a chlorination reaction with a mechanism. This is one where you're asked to draw some mechanistic steps in a chlorination of an alkane. So the alkane that you're given, first of all, you're given this background information. You're saying we're starting with cyclopropane, which is an alkane, and we're putting this in with chlorine, and we're going to be giving it some activation energy with UV light or light energy. And the products that come out of this are a chlorinated alkane and HCl. So that's the overall process. That's what you get when you put a chlorine on a cyclopropane ring, but there's a mechanism, and the mechanism has steps. There's an initiation step, which is the chlorine breaking into 2 radicals, and so you're asked to draw the initiation step for this. So the initiation step in a halogenation reaction is where the chlorine or the bromine molecule breaks into 2 pieces to give 2 radicals. And this is what happens when you put light energy into it. This molecule absorbs a photon, and that causes it to fracture. The bond breaks homolytically. The electrons in the chlorine-chlorine bond, each one goes to a different chlorine, and so you get these 2 Cl dots. So that's an initiation reaction because it's producing radicals where there were none before. And that's the first thing you were asked. Draw the initiation step of the mechanism. Now, you might be asked to draw propagation steps, in which case just you got to make sure you follow the directions. There's a question in the back. Oh, no, I'd be fine with that. It's this one, there was no need for that. The truth is, you got to put energy in to break a bond, but that's specified up here, so I think that's good enough. So yeah, don't worry about that. But yeah, anyway, you do need energy to break the bond, but that's not something I think I would test on or require you to show. And then the question asks you to show one of the 2 propagation steps. And since there are two of them, I'm going to show both of them just to get it. You only needed to show one in this question. But the first propagation step is you take the Cl dot that you made in the first step, and you have it react with the alkane. So the alkane is this molecule. It has CH bonds, and the Cl dot grabs one of them. So what I'm saying with these, and I'm going to move this arrow over so it goes more to the middle of the bond. What I'm saying with these curved arrows is that Cl dot grabs an H dot, and they get together and they form a new Cl hydrogen bond. So the product of this reaction is going to be HCl. Then the other electron in the carbon-hydrogen bond goes to carbon, and that produces this new radical species. This is not creating a new radical or destroying an old radical, but just transforming a radical from one atom to another, one spot to another. So that's what a propagation reaction involves. So that's the first propagation reaction, and this explains one of the two products. So HCl is one of the two products that we're getting, and so the first propagation step produces that. Now we're going to take this and move this over to the next board to do the second propagation step. And that radical that was the product of the first propagation step, we're going to use that in the second propagation step as our key reactant. So propagation step 2. Propagation step 2. So step 1 produced this radical, and the thing about these chain reactions is the product of one reaction is the reactant in another one. So the way chain reactions work are a reaction happens, produces a reactive intermediate, and that reactive intermediate goes on to do another reaction that produces another reactive intermediate. And basically every reaction produces a radical that can go and do a subsequent reaction. That's what a propagation reaction is. And then what this does is, what does that react with? Well, it can react with a molecule of Cl2, because not all of the chlorine gets converted to radicals in the initiation step. So that initiation step that I showed on the previous board where light was absorbed by the chlorine and it splits it into two radicals, that's a reaction that produces just a little bit of radicals, but mostly the chlorine remains intact. So there's plenty of chlorine around for this radical to find. And what it does is it grabs a Cl dot. You can show that with two fishhook arrows coming together. And then the other electron in the chlorine-chlorine single bond goes to the other chlorine. And so what this does is gives then the other major product in the reaction and reproduces a Cl dot, which can be the reactant in the first propagation reaction. So once you form Cl dots, what happens is first propagation reaction, second propagation reaction, first propagation reaction, second, it goes like that. It's just like they happen one after another over and over and over again until you get lots of chlorination products, or until two radicals bump into each other in solution. So termination reactions, you're not asked about these, but let's talk about them anyway. Termination reactions are any ones where two radicals get together. It could be two Cl dots getting together. So a Cl dot and a Cl dot. If they bump into each other, their electrons can pair up and they'll form Cl2. That's a real energetically favorable reaction because you make a bond where there wasn't one before. You could also get the carbon radical reacting with a Cl dot. So this is another one you could imagine happening, two radicals of different types coming together, and that would make one of the two products. It's not a major contributor to the overall amount of product because it doesn't happen very often, but it does produce some product. And then the other possibility, if you look at all the radicals that are involved in this reaction, there are carbon radicals like this. So you could get two of these cyclopropyl radicals coming together, and they would form, this is a kind of a funny looking molecule, but you would form a little bit of this. Cyclopropyl cyclopropane. It looks strange, but it's a real byproduct. So you get a bit of this. Okay. Yeah. What do you want to? Okay. So let's talk about the next question, which is an allylic bromination question. So allylic bromination is one where you put an alkene in, carbon-carbon double bond containing molecule, with this molecule N-bromosuccinimide, and you give it a little activation energy. So here is the molecule you're given to work with, and the one you're asked to have it react with is N-bromosuccinimide, and here is the structure of that molecule. You can recognize it because it's got the nitrogen-bromine bond in it, and that's kind of unusual. We don't see that too often. It's a weak bond, and this is a one that likes to donate a bromine, a Br dot. And what can happen is there's allylic positions here, 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 and here that are all subject to getting abstracted by, the H's on there can get abstracted by a radical to produce a dot on these carbons. That's especially stable because it's resonance stabilized. It's in an allylic position. And the molecule has a mirror plane of symmetry through it. So the one side and the other side are reflections. So what you should do is consider all the possible radicals that you can get. So first one I'll consider is what's it like if you get a dot on one of the methyls? And that putting a dot here would be the same as putting a methyl dot or a CH2 dot up here because it'd be symmetrical. That's one of the radicals, but there's a resonance structure associated with this that you have to think about, which is like this. And that would produce this radical, which is just a resonance structure of this one up here. So these two structures are the same molecule, it's just their electrons are arranged differently. But they can give unique products. So each one of these could give a bromide where the dot is, because the last step in the mechanism is the dot grabs a Br dot or grabs a Br atom and you get a carbon-bromine bond. So just when you get this far, basically each one of these becomes a bromide where the dot is. The other allylic position is the one within the ring. So I'm going to draw that one next. You could put a dot right there, for example. If you abstracted one of the H's, there are two of them. If you abstracted one of them that's in that position, you'd get this radical here. And there is a resonance structure for this one. That's the thing about allylic bromination is there's always a resonance structure because it's in an allylic position. And the resonance structure for this radical looks like this, where there's a double bond there and a dot right there. So these two can also give bromides. So if you have the set of radicals, then to get the set of allylic bromides, all you have to do is just draw the structures, but change the dot to a bromine. So I'm going to skip that step because I want to save time so we can go on to some other things. But think about all of these as being potential precursors to bromides. All right, there's one on polymers that I want to talk about here because this is a good one. Fits in with radical chemistries because a lot of polymers are produced by radical polymerization. And that's the case with this one. You're given a bit of a structure here. You're asked to decide what kind of monomer it would come from. And you're told this molecule is polycyanoacrylate, which is superglue. So it looks like an intimidating structure. You know, there's a lot of atoms and everything, but your job would be to find the smallest repeating unit. So if you study this thing, what you'll see is it goes carbon with a C triple bond N and ester. Then it goes CH2. Then it goes carbon, CN, ester. CH2, carbon, CN, ester. So every other carbon is the same. And the smallest repeating unit would be any of these. So I'm just going to lasso out this one and say that's the part that repeats over and over again. There's one of these units over here, and there's one to the right, but this just comes back over and over and over again. This is the thing you have to start with. So the monomer that would have produced this has to have all those atoms in it. It has to have the carbons in the main chain. It has to have an ester on the carbon. It also has to have the CN on that carbon. It has to have H's on that carbon. And here's the thing that a lot of people forget. It has to come from an alkene. So that's how you decode these, basically. If you put this cyanoacrylate molecule in with an initiator, you get polycyanoacrylate. And basically then you've got a glue. The next one is a recycling question. So it gives you a bit of a polymer and asks you, what is the name of this thing and what's its recycling symbol? So let's just go over this really kind of quickly. Here is a polymer. This is the polymer nomenclature. It's showing us the repeating unit, and that's in brackets, and then there is an N, which indicates it repeats a whole bunch of times, whatever N is. It can be hundreds of units, actually. So what does this come from? It comes from a monomer that would have these atoms in it and a double bond here. But this molecule is got recycling symbol number 5. So this has got that, and then there's a PP below it because this is what's called polypropylene. And if you want a quick way to remember this stuff, here's, when you're studying, you'd probably come up with this on your own, like a way to remember this, but the polymers are all the same except for an R group. That's the only thing that's different about them. So if you just want to remember what the R group is, that can tell you what kind of polymer you have. So when R is equal to hydrogen, the polymer is either 2, that's HDPE for high density polyethylene, or 4, LDPE for low density polyethylene, and they're not exactly the same. There's subtle structural differences. Low density polyethylene has some branching, but when the R is H, it belongs to these two families. When the R is equal to Cl, the polymer is V, that's polyvinyl chloride, PVC. When it is methyl, the recycling symbol is 5, and it has a PP below it for polypropylene. And when the R group is a phenyl group, benzene ring, this is got a 6, and there's a PS below it, which stands for polystyrene. So that's what you need to know, is the polymers are very similar. It's just the R group that's different. It's either H or methyl or chlorine or phenyl. Question? No, 1 or 7 we haven't talked about. 7 is not a unique one. It's a catch-all term for anything that's like not 1 through 6. And number 1 we haven't talked about, but we will get to that later on in the semester because it's a different kind of polymer. It's a polyester, so it's different chemistry that puts it together. Another question.
So then looking at this as a question on a test, if the CH3 was an H, how would we be able to tell the difference between the two or four?
Okay, yeah, you wouldn't be able to. It would be either one or the other. So I would, I wouldn't ask you that because it'd be sort of ambiguous. There wouldn't be one unique answer. So yeah, probably what I would do is, I might say, what's the R group if it's 2 for this thing, and then you'd have a unique answer. But going the other way, it could be either this or this. So yeah, that wouldn't be a good exam question. I try to make these things so it's as straightforward as possible, so it isn't confusing about what I mean. I don't always succeed, but I try. All right, we got a little bit more time left here. Conjugation. This was the next topic that we hit when we did the new chapter on conjugation and the Diels-Alder reaction. There were questions about stability, and one of the big take-home messages from that chapter was that conjugation stabilizes dienes. It stabilizes other things too, but there was a series of molecules called the elamines. These are natural products that have lots of double bonds in them, and the locations of the double bonds influence their stability because it determines whether or not they're conjugated. So this is one of the elamines that was listed as and this one's called the alpha elamine, but not that really matters. But in terms of stability, the thing to look for when you've got a molecule that's got lots of double bonds is, are there any that are conjugated? So this would be overlapping p orbitals on adjacent atoms. So this one's got, let me get my orange chalk out here, draw a real bold orange kind of lasso around that. That diene is conjugated. This alkene is not conjugated because there's an sp3 hybridized atom between it and the others. So that's what's called an isolated alkene, and this is a conjugated couple of alkenes. And then there's some other elamines too, but the key is that this is the only one that's conjugated. So conjugation stabilizes the diene. The other thing that leads to stability differences is how highly substituted are they. So if you look at this double bond, it's tetrasubstituted. It's got 1, 2, 3, 4 carbon groups on it, which makes it really stable. This one has 1, 2, 3 carbon groups on it, which makes it really stable. So this one was the most stable elamine for those two reasons, but resonance is really the big one. And that's the theme of the chapter. So we're going to have things where you have to identify conjugation in a molecule. So look for that. There was another question that asked about a related topic, which is hybridization. So there was this kind of large molecule that was shown. It's a drug that is used to treat high blood pressure, and it's got this structure. There's an H here, and then there's a aromatic ring up here with a chlorine on it. And then over here there was an ester with an ethyl group there. And then over here there's a double bond there, CH2O with an NH2 over here. And then a nitrogen with a lone pair here, double bond here, methyl, and then an ester over here. And a few of these positions were indicated with arrows. So there was an arrow pointing to this oxygen saying, what's its hybridization? There was an arrow pointing to this oxygen asking you, what's its hybridization? And then there was an arrow pointing to the nitrogen. We had to identify hybridization there. And then there was, well, that was it. There were 3 of them. So we used to just use electron group counting to determine hybridization. We saw 2 groups, we'd say sp. If there were 3 groups, we'd say sp2. And if there were 4 groups, electron groups, we'd say sp3. That holds except for situations where the atom is part of an XYZ system. So this is really all about your recognizing this XYZ rule. So XYZ, when you have a situation like this where there's a double bond and next door there's a Z atom where it has a lone pair, the Z atom is sp2 hybridized. So this fits the definition of XYZ. So that oxygen is sp2. And that's true of all carboxylic acid oxygens, all ester oxygens. They're sp2 hybridized. That allows them to be conjugated and the electrons are shared. This one does not have any adjacent double bond. So it has 4 electron groups. It's got 2 lone pairs. By the way, this one has 2 lone pairs too. They weren't shown, but if you just counted electron groups and saw there were 4 and didn't remember the XYZ rule, you'd probably think sp3, but this one's sp2. This one's got 4 electron groups, but there's no adjacent double bond. So this one doesn't fit that pattern of XYZ group. And so its most stable orientation is just to put the groups as far apart as possible, which is tetrahedral arrangement and sp3 hybridization. So this is just a standard sp3 hybridized oxygen with 4 groups, electron groups. The nitrogen here is part of an XYZ pattern, XYZ, and it is therefore sp2. So understanding that rule is one of the things we talked about. Then you get into Diels-Alder and stuff, and so we're not going to have time to go over that, but it was a little more recent, so I'm hoping it still sticks in your head. I will see you on Monday for the exam. Have a good weekend.